Why doesn't Earth get too cold? It is a simple question, almost childlike in its phrasing, and yet it opens into something vast. Space is not warm. It is not even cool in the way we understand cool air on a winter night. The average temperature of the universe is about 2.7 degrees above absolute zero, a faint background warmth left over from the early cosmos. That is roughly minus 270 degrees Celsius. In most directions, if you were floating between the stars, there would be almost nothing around you. No air, no pressure, no blanket of gas to hold warmth close. And yet, here on Earth, oceans remain liquid. Rain falls. Snow melts. Most nights, even the coldest ones, do not approach the emptiness of space. So why doesn't Earth get too cold? To begin answering that, it helps to understand something gentle but important. Cold in space does not behave the way cold behaves on Earth. In the absence of air, there is no wind to pull heat away from your skin. There is no icy breeze. There is only radiation. The slow release of energy in the form of invisible infrared light. Every object that has warmth gives off this faint glow. Your hands do it. The ground does it. The planet does it. Earth is constantly radiating heat into space. At the same time, the sun is constantly delivering energy toward us. Sunlight arrives as visible light and ultraviolet radiation. When it reaches Earth's surface, it is absorbed by land, water, and atmosphere. That absorbed energy warms the surface. The warm surface then re-emits that energy outward again as infrared radiation. If this were the whole story, Earth would lose heat quickly. Without any moderating influence, calculations show that our planet's average surface temperature would sit near minus 18 degrees Celsius. That is well below the freezing point of water. Oceans would become ice-covered. The planet would resemble a brighter version of present-day Mars. But that is not what we observe. Instead, Earth's actual global average temperature sits near 15 degrees Celsius. That difference of more than 30 degrees is not random. It is not accidental warmth. It is the result of a physical process happening quietly above our heads at all times. Before we move further into that explanation, I want to pause here for just a moment. If you enjoy these quiet journeys, you're welcome to subscribe, and if it feels natural, to leave a comment sharing where you're listening from tonight. It helps others find their way to this calm corner of the world, one sleepy traveler at a time. The quiet continues here, just as it is. Now, back to the question. To understand why Earth does not become as cold as space, we can look at a nearby example. The Moon orbits only about 384,000 kilometers away. It receives nearly the same sunlight Earth does, and yet its temperature swings wildly. During lunar day, the surface can reach around 127 degrees Celsius. During lunar night, it can fall to minus 173 degrees. The Moon has no substantial atmosphere, no thick layer of gases to slow the loss of heat. When sunlight stops striking its surface, the warmth simply radiates away into the vacuum. Heat leaves quickly when nothing stands in its path. Earth is different. Between the surface and space lies a layered atmosphere extending hundreds of kilometers upward. Most of that atmosphere is made of nitrogen and oxygen, gases that are largely transparent to infrared radiation. but mixed within them are small amounts of other gases that interact with outgoing heat in a subtle way. They absorb certain wavelengths of infrared radiation and then re-emit it in all directions, including back toward the surface. This does not stop heat from leaving entirely. Earth still radiates energy into space, but it slows the process. It delays the escape. It creates a kind of thermal balance where incoming solar energy and outgoing infrared radiation reach an equilibrium. The result is not perfect warmth. It is regulated warmth. Earth is never isolated from space. It is always glowing faintly in infrared, always exchanging energy with the vast cold beyond its atmosphere. But because of this steady balance between incoming sunlight and partially retained heat, the planet remains temperate instead of frozen. A quiet exchange is happening constantly, above us and beneath us, even now. And tonight, we begin to explore it. When we speak about something being cold, we often imagine a sensation. A sharp wind against the face, frost forming on glass, the quiet sting in the air before snow begins to fall. But in physics, cold is not a feeling. It is a measurement of motion. Temperature is simply the average motion of molecules. When molecules move quickly, we call that warmth. When they move slowly, we call that cold. There is no separate substance called cold. There is only less motion, less internal vibration, less energy being exchanged between particles. In space, there are very few particles at all. The region between planets is not filled with air. It is an almost perfect vacuum. That means there are so few atoms and molecules present that there is very little to collide with anything else. And without collisions, there is no conduction. Without moving air, there is no convection. Two of the three main ways heat moves simply cannot operate in empty space. Only radiation remains. Radiation does not require matter. It does not require contact. It does not require wind. It is energy traveling as electromagnetic waves, moving outward at the speed of light. Every object with a temperature above absolute zero emits radiation. The warmer it is, the more it emits. The Stefan-Boltzmann relationship tells us that the energy radiated increases rapidly with temperature, rising with the fourth power of temperature in Kelvin. This means even small increases in surface warmth produce significantly more outgoing radiation. Earth, at roughly 288 Kelvin on average, is constantly glowing in infrared light. We cannot see this glow with our eyes, but instruments can detect it easily. Satellites measure the steady outward flow of infrared energy leaving the top of the atmosphere. It is not dramatic. It is not visible flame. It is a quiet, continuous release. If there were nothing to interrupt this process, Earth would cool until it reached a balance point where the energy leaving matched the energy arriving from the sun. That balance point, without atmospheric influence, would settle near minus 18 degrees Celsius. At that temperature, the outgoing infrared radiation would equal the incoming solar radiation after accounting for reflection. That balance is called radiative equilibrium. It is not a fixed comfort setting. It is a mathematical outcome. Incoming energy must equal outgoing energy over time, or the temperature will shift until it does. This is why space does not pull heat away from Earth in an aggressive sense. There is no suction. There is no cold wind in the vacuum waiting to steal warmth. There is only the steady emission of radiation outward, driven by temperature difference. Heat flows from warmer objects to colder surroundings because of physical law, not because cold reaches inward. You can picture it as a faint, invisible glow rising from the surface and moving outward in all directions. Each square meter of Earth emits roughly 390 watts of infrared energy at average surface temperature. Some of that energy escapes directly into space. Some interacts with atmospheric gases. Some is redirected. The process is ongoing and balanced. During nighttime, when sunlight no longer reaches a particular region, incoming energy briefly drops to zero. Outgoing radiation continues. The surface cools. Molecules slow, but the cooling is not instantaneous. The ground holds stored heat. The air above interacts with that warmth. Water vapor and clouds absorb some outgoing infrared and re-emit it. Cooling becomes gradual, rather than abrupt. On the Moon, without air or water, that stored heat dissipates far more quickly. Surface temperatures plunge sharply once sunlight disappears. On Earth, the descent is softened by layers of interaction. So cold, in the planetary sense, is not an active force. It is what happens when energy leaves faster than it arrives. Earth does not get too cold because energy does not leave unchecked. Radiation moves outward, yes, but the atmosphere modifies its path. The system adjusts continuously. Temperature is not held in place by a barrier. It is stabilized by exchange. At every moment, trillions upon trillions of molecules in the air above you are absorbing and emitting infrared radiation. The movement is invisible, but it is measurable. The balance is dynamic, but it is real. Warmth here is not an accident. It is the result of motion, radiation, and equilibrium unfolding quietly across an entire planet. The Moon offers a quiet comparison. It circles Earth at a distance that feels small on a cosmic scale, only about 384,000 kilometers away. Sunlight reaches its surface almost as strongly as it reaches ours. The amount of solar energy falling on a square meter of lunar soil at noon is nearly the same as the sunlight striking a square meter of desert on Earth. And yet the temperature behavior could not be more different. During lunar daytime, when the sun hangs high above the surface, temperatures can climb to around 127 degrees Celsius. That is hot enough to boil water rapidly. The grey dust absorbs sunlight directly, warming without interference. There is no atmosphere to scatter the light, no clouds to reflect it, no air to circulate heat away. The surface simply absorbs and heats. But the Moon rotates slowly. One full lunar day from sunrise to sunrise lasts about 29.5 Earth days. That means the sun shines continuously on a given region for roughly 2 Earth weeks. The soil grows hotter and hotter because there is little to moderate the buildup. Then the sun sets, and darkness lasts for another 2 Earth weeks. When night arrives on the Moon, temperatures fall to about minus 173 degrees Celsius. Without air to trap outgoing infrared radiation, without water to store and release warmth, the surface cools rapidly. heat radiates outward directly into space. Molecules lose energy. Motion slows dramatically. The swing between lunar day and lunar night is extreme because there is almost nothing standing between the surface and the vacuum. No atmosphere means no greenhouse effect. It also means no convection, no wind, no redistribution of heat from warmer regions to cooler ones. Each patch of surface is largely on its own. If Earth behaved like this, daytime temperatures would spike sharply, and nighttime temperatures would plunge far more deeply. But they do not. Part of the reason lies in rotation. Earth spins once every 24 hours. Sunlight moves across the surface quickly compared to the moon's slow cycle. Night does not last 2 weeks. It lasts hours. That shorter period limits how much cooling can occur before sunlight returns. But rotation alone is not enough to explain the difference. Even during a single night, the moon's temperature falls much more dramatically than Earth's does in the same span of time. The key difference is the presence of an atmosphere. Earth's atmosphere acts as a medium for interaction. As the surface cools at night by radiating infrared energy upward, some of that outgoing radiation is absorbed by gases such as water vapor and carbon dioxide. Those gases then re-emit infrared radiation in all directions, including back downward toward the surface. This does not eliminate cooling, it slows it. Instead of heat escaping directly and completely into space, part of the outgoing energy lingers briefly in the atmosphere. It is redistributed. It is delayed. Clouds play a role as well. On cloudy nights, temperatures often remain warmer than on clear nights. This is because cloud droplets and ice crystals absorb outgoing infrared radiation efficiently and re-emit it downward. The effect is measurable. Meteorologists can track the reduced rate of cooling beneath cloud cover compared to open skies. On the moon, there are no clouds. There is no air at all. So when sunlight stops, cooling begins immediately and continues without moderation. The moon teaches something simple but powerful. Solar energy alone does not determine surface temperature. The way energy is retained and redistributed matters just as much. The same sunlight can produce wildly different thermal outcomes depending on the presence or absence of atmosphere. Earth does not get too cold because its heat does not escape unfiltered. The surface and atmosphere are engaged in constant exchange. Energy flows upward, is partially redirected, and then continues outward. Cooling happens, but it happens within a layered system rather than in isolation. Looking at the moon from Earth, it appears calm and still. A silent grey sphere suspended against black. But thermally, it is unstable, swinging between extremes. Earth's stability is quieter, less dramatic, but deeply significant. Where the moon radiates into emptiness alone, Earth radiates through a veil of gases that reshape the journey of its heat, and that difference changes everything. If Earth had no atmosphere, the difference would be immediate. You can imagine the oceans still in place, the continents still rising and falling as they do now, the rotation unchanged, the distance from the sun exactly the same. The only missing element would be the thin layer of gas that surrounds the planet, extending upward in gradually thinning bands, Without that layer, sunlight would still arrive. About 1,361 watts of solar energy per square meter reach the top of Earth's atmosphere. That value, known as the solar constant, would not change simply because the air was gone. The surface would still absorb visible light. The ground would still warm during the day. But once the surface absorbed that energy, it would release it again directly into space as infrared radiation. With no greenhouse gases to absorb outgoing infrared wavelengths, and no atmospheric molecules to re-emit radiation downward, the heat would escape efficiently. The energy balance would shift. Climate models allow scientists to estimate what the average global temperature would be under those conditions. The result is about minus 18 degrees Celsius. That is the temperature Earth would settle into if it absorbed sunlight and radiated energy outward with no atmospheric infrared absorption. Minus 18 degrees Celsius is not as extreme as the lunar night, but it is far below freezing. Large portions of the oceans would freeze at the surface. Ice would expand across continents. The hydrological cycle as we know it would collapse. Water vapor would decrease sharply in the absence of warmth, reducing one of the most important greenhouse contributors even further. Cooling would reinforce itself. There is a physical concept called positive feedback. In climate terms, this refers to a process where an initial change triggers additional changes that amplify the original effect. Ice reflects more sunlight than dark ocean water. This reflectivity is known as albedo. Fresh snow can reflect up to 80 or 90% of incoming sunlight. Open ocean reflects far less. If the planet cooled and ice expanded, more sunlight would be reflected back into space. Less energy would be absorbed at the surface. That would promote further cooling. The feedback would push the system toward an even colder equilibrium. Earth has experienced periods in its distant past when ice covered much larger areas than today. During certain intervals hundreds of millions of years ago, evidence suggests that glaciers reached tropical latitudes. These so-called snowball Earth events show how sensitive global temperature can be to atmospheric composition and solar input. But even during those cold phases, Earth retained an atmosphere. Without any atmosphere at all, the transition would not be gradual over millions of years. It would be immediate in geological terms. The surface temperature would fall until the incoming solar radiation equaled outgoing infrared radiation, with no moderating delay. It is important to notice that the atmosphere itself is not thick in absolute terms. If you compressed all of Earth's atmospheric gases to sea level pressure evenly across the globe, the resulting layer would be only about 8 to 10 kilometers thick on average. Compared to Earth's radius of over 6,300 kilometers, that is extremely thin. And yet that thin layer changes everything. Within it, gases absorb specific wavelengths of infrared radiation emitted by the surface. Carbon dioxide absorbs strongly around 15 micrometers. Water vapor absorbs across multiple bands. Methane and nitrous oxide contribute smaller but measurable effects. These absorptions are not uniform. They occur at precise frequencies tied to molecular structure. Molecules vibrate in response to infrared photons. They then re-emit energy, sometimes upward, sometimes downward. This constant absorption and re-emission slows the rate at which energy leaves the surface. The atmosphere does not act like a solid blanket. It does not trap heat in a sealed container. Instead, it modifies the path of radiation. It lengthens the time heat spends within the Earth atmosphere system before escaping to space. Without that delay, the surface would cool until it reached the colder radiative equilibrium. So when we ask why Earth does not get too cold, we are really asking why the planet does not radiate energy away without resistance. The answer begins with that thin veil of gas suspended above us, interacting invisibly with outgoing infrared light, altering its journey by fractions of seconds that accumulate across an entire globe. A difference of tens of degrees emerges from processes happening at the scale of molecules. And all of it unfolds quietly, above every ocean and every field, every night and every day. To understand why Earth does not drift toward deep cold, it helps to look at the planet as a whole system of exchange. Energy arrives, energy leaves, and the balance between those two flows determines temperature. The sun emits energy across a broad range of wavelengths, but the majority that reaches Earth arrives as visible light and near-infrared radiation. When this sunlight encounters the top of the atmosphere, not all of it reaches the ground. Roughly 30% is reflected back into space by clouds, atmospheric particles, and bright surfaces such as ice and snow. This reflectivity, known as planetary albedo, reduces the amount of energy that must be balanced. The remaining 70% is absorbed by the atmosphere, the oceans, and the land surface. Absorption increases molecular motion. Molecules begin moving more quickly. Surfaces warm, but energy cannot simply accumulate forever. If more energy entered than left, the temperature would rise continuously. If more left than entered, temperature would fall. So over long periods, the planet adjusts until incoming solar radiation equals outgoing infrared radiation. This balance is called energy equilibrium. It is not static in the short term. Daily and seasonal variations shift the numbers constantly, but averaged across the globe and over time, the equality must hold. The outgoing side of the equation is governed by thermal radiation. Every object with a temperature emits radiation proportional to the fourth power of its temperature in Kelvin. This relationship means that as Earth's surface warms even slightly, the amount of outgoing infrared radiation increases noticeably. The system naturally pushes back against warming by radiating more energy. And if the surface cools, outgoing radiation decreases, allowing energy to accumulate again. This is a stabilizing tendency built directly into physics. You can picture it as a gentle self-correcting glow. If the surface becomes warmer than equilibrium, it shines more intensely in infrared. If it becomes cooler, the glow weakens. The energy flow adjusts accordingly. However, this glow does not travel straight into space without interaction. As infrared radiation rises from the surface, it passes through layers of air. Some wavelengths move through nitrogen and oxygen almost unhindered, but other wavelengths are absorbed by greenhouse gases. The absorbed energy temporarily increases the vibrational motion of those gas molecules. They then re-emit radiation in random directions. Some of that re-emitted radiation continues upward. Some travels sideways. Some returns downward. The net effect is that the average altitude from which Earth radiates energy into space shifts upward. Instead of radiation escaping directly from the surface, much of it escapes from higher, cooler layers of the atmosphere. And because those higher layers are colder than the surface, they emit less radiation for a given temperature. This detail is important. Colder objects emit less energy than warmer ones. So if the effective radiating layer is colder, the outgoing energy initially decreases. To restore equilibrium, the surface must warm until the outgoing radiation from that higher altitude matches the incoming solar energy once again. The system rebalances at a higher temperature. This is how atmospheric insulation functions, not by blocking energy completely, but by raising the altitude from which radiation effectively escapes. Even now, at this moment, satellites measure Earth's outgoing infrared radiation. They detect patterns tied to clouds, water vapor concentrations, and carbon dioxide absorption bands. The data show that radiation escapes unevenly across wavelengths, with certain frequencies partially absorbed and others passing through atmospheric windows more freely. There are literal infrared windows in the atmosphere where radiation escapes with minimal absorption. Much of the infrared radiation can pass outward more directly. These windows prevent complete heat trapping. They ensure that Earth continues to cool into space efficiently enough to maintain balance. Without those windows, temperatures would climb far higher. So the system is neither sealed nor fully open. It is selective. Energy flows continuously through it, slowed in some channels, accelerated in others, adjusted by physical law rather than intention. Earth does not get too cold because the outgoing flow of energy is moderated, not eliminated. The planet radiates steadily, but the atmosphere reshapes that radiation path just enough to hold warmth within a narrow range. And in that narrow range, liquid water persists, oceans circulate, and the surface remains far above the frozen stillness of space. Up to this point, we have been describing energy leaving. Now it helps to slow down and describe what happens to energy after it arrives. Sunlight travels across space as visible light, ultraviolet radiation, and near-infrared waves. When it reaches Earth, most of it passes directly through the atmosphere. The air above us is largely transparent to visible light. That is why we can see the sun clearly on a cloudless day. The photons travel through nitrogen and oxygen without being absorbed in large amounts. Light enters. It reaches the ground. It reaches the ocean. It reaches rooftops, forests, deserts, and fields. When sunlight strikes these surfaces, it is absorbed. Darker surfaces absorb more. Lighter surfaces reflect more. But wherever light is absorbed, molecular motion increases. The surface warms. A warm surface cannot keep that energy indefinitely. Every warm object emits radiation, but the type of radiation it emits depends on its temperature. The sun, at about 5,500 degrees Celsius at its surface, emits mostly visible light. Earth, at an average temperature near 15 degrees Celsius, emits radiation at much longer wavelengths, primarily in the infrared part of the spectrum. So the energy changes form. visible sunlight arrives, infrared radiation leaves. This is the core transformation. The greenhouse effect begins with that shift. When the surface re-radiates absorbed energy upward as infrared light, that radiation travels towards space. If the atmosphere were perfectly transparent to infrared radiation, most of it would pass through and escape. But the atmosphere is not fully transparent at those wavelengths. Certain gases have molecular structures that allow them to absorb infrared radiation at specific frequencies. When an infrared photon matches the vibrational frequency of a molecule, it can be absorbed. The molecule begins vibrating more strongly. It gains energy. It does not hold that energy permanently. Within fractions of a second, the molecule re-emits radiation. That re-emitted radiation travels in random directions. Some of it continues upward, some of it moves sideways, and some of it travels downward, back toward the surface. This downward component matters. It does not add new energy to the system. It redistributes energy that was already there. But by redirecting some outgoing infrared radiation back toward the surface, it slows the rate at which heat escapes into space. Heat lingers. This is the greenhouse effect in its simplest physical form. Light enters easily. Heat leaves more slowly. The name can be misleading. A physical greenhouse traps warm air by preventing convection. Earth's atmosphere does not operate that way. Air is free to circulate. Wind moves heat horizontally and vertically. What slows cooling is not trapped air, but selective absorption and re-emission of infrared radiation. The atmosphere behaves less like glass and more like a semi-transparent filter. Some wavelengths move through freely. Others are partially absorbed and redirected. Because of this filtering, the average altitude from which Earth radiates energy into space is higher than the surface. And higher altitudes are colder. Colder layers emit less radiation at a given temperature. So to restore balance between incoming sunlight and outgoing radiation, the surface must warm until enough infrared energy escapes from those higher layers. The effect is measurable. Without greenhouse gases, the calculated global average temperature would sit near -18 degrees Celsius. With the naturally occurring greenhouse effect, the actual average is around 15 degrees Celsius. That difference of roughly 33 degrees arises from molecular interactions happening invisibly in the air. No intention, no design, just physics. You can picture sunlight entering the atmosphere in long, straight paths, striking the surface and warming it. Then imagine infrared radiation rising upward like a faint, invisible glow. Some of that glow passes through clear atmospheric windows. Some is intercepted, absorbed, and redirected. The surface receives a small portion back again. Not enough to prevent cooling entirely, but enough to soften it. Earth does not get too cold because the energy leaving the surface does not depart all at once. It moves through layers of air that reshape its journey. The heat is not sealed in. It is delayed, redistributed, and balanced against the steady input from the sun. Light enters, heat lingers, and in that lingering, the planet remains temperate instead of frozen. Not all gases in the atmosphere behave the same way. Most of the air around you, if you could gather it and separate it into parts, would be nitrogen and oxygen. Together, they make up about 99% of the atmosphere. Nitrogen accounts for roughly 78%. Oxygen makes up about 21%. These molecules are simple. Each nitrogen molecule contains 2 nitrogen atoms bonded together. Each oxygen molecule contains 2 oxygen atoms bonded together. Because of their symmetry, these molecules do not absorb infrared radiation efficiently. Infrared absorption depends on changes in electric charge distribution as a molecule vibrates. Nitrogen and oxygen are symmetrical and nonpolar. When they vibrate, they do not create strong fluctuating electric fields. Infrared photons pass through them with little interaction. They are largely transparent to the wavelengths of radiation emitted by Earth's surface. So if nitrogen and oxygen were the only gases present, the atmosphere would allow most outgoing infrared radiation to escape directly into space. But they are not alone. Mixed within the air are smaller concentrations of gases with more complex molecular structures. These molecules bend, stretch, and twist in ways that allow them to absorb infrared radiation effectively. Water vapor is the most abundant greenhouse gas. Its concentration varies widely depending on location and temperature. Warm air can hold more water vapor than cold air. This is why humid tropical regions contain more atmospheric moisture than dry polar regions. Water vapor absorbs infrared radiation across a broad range of wavelengths. It plays a major role in slowing heat loss from the surface. Carbon dioxide is present at much lower concentrations, currently a little over 400 parts per million. That means for every million air molecules, about 400 are carbon dioxide. Despite its small proportion, carbon dioxide absorbs strongly at specific infrared wavelengths, especially around 15 micrometers. That absorption band overlaps with part of Earth's outgoing radiation spectrum, making it significant in energy balance. Methane is even less abundant, measured in parts per billion. Yet methane molecules absorb infrared radiation very efficiently in certain bands. Over short timescales, molecule for molecule, methane can trap more heat than carbon dioxide. However, methane does not persist as long in the atmosphere. Chemical reactions gradually break it down. Nitrous oxide is present in even smaller amounts, but it also contributes to infrared absorption. Like methane, its impact depends on both its efficiency in absorbing radiation and its atmospheric lifetime. What these gases share is asymmetry in their molecular structure. Carbon dioxide contains 1 carbon atom, bonded to 2 oxygen atoms. Though linear in shape, its vibrational modes allow for temporary dipoles that interact with infrared radiation. Water vapor has a bent shape, creating a permanent dipole moment. That bent geometry makes it highly effective at absorbing and emitting infrared radiation. Molecules vibrate in response to specific wavelengths. When infrared photons match those vibrational frequencies, absorption occurs. The molecule gains energy, increases its motion briefly, and then releases radiation again. The process is selective. Certain wavelengths are strongly absorbed. Others pass through more easily. This is why the atmosphere has infrared windows where radiation escapes more freely. It is also why increasing the concentration of greenhouse gases changes the balance subtly but measurably. More absorbing molecules mean more opportunities for infrared photons to be intercepted and redirected before escaping. water vapor differs from carbon dioxide in one important way. Its concentration is strongly tied to temperature. Warmer air holds more moisture. So as the surface warms, water vapor increases, amplifying the greenhouse effect. As the surface cools, water vapor decreases, reducing that effect. This makes water vapor both a greenhouse gas and a feedback mechanism. Carbon dioxide, by contrast, is not controlled directly by temperature in the same short-term way. Its concentration depends on biological processes, ocean exchange, and geological cycles. When we ask which gases matter in preventing Earth from becoming too cold, the answer is not the bulk of the atmosphere. It is the small fraction made of molecules capable of interacting with infrared radiation. Nitrogen and oxygen create the pressure and bulk of the air, allowing for weather, clouds, and convection. But it is water vapor, carbon dioxide, methane, and nitrous oxide that reshape the path of outgoing heat. A thin scattering of asymmetrical molecules in a vast sea of symmetrical ones makes the difference between -18 degrees and 15 degrees. A difference measured not in percentages of air, but in vibrational physics unfolding invisibly above every horizon. If you could step back far enough to see Earth from a distance, the atmosphere would appear as a faint blue halo wrapped around the curve of the planet. It is thin compared to Earth's size, but it is continuous. A layered envelope of gas held in place by gravity, gradually thinning with altitude. Pressure is highest at the surface and decreases as you move upward. About half of the atmosphere's total mass lies within the lowest 5 to 6 kilometers. By the time you reach 100 kilometers above the surface, the air is so thin that it begins to merge with the vacuum of space. Thickness matters, not only in terms of composition, but in terms of pressure and density. The more massive an atmosphere is, the more molecules there are available to absorb and re-emit infrared radiation. Higher pressure means more collisions between molecules. Energy is transferred more frequently. Heat lingers longer before escaping. Venus provides one extreme example. Its atmosphere is composed mostly of carbon dioxide and is more than 90 times as massive as Earth's. Surface pressure on Venus is about 92 times greater than at sea level on Earth. The thickness of that atmosphere creates an intense greenhouse effect. Infrared radiation emitted by the surface is absorbed and re-emitted repeatedly before it can escape to space. The effective altitude from which radiation leaves the planet is very high in the atmosphere, where temperatures are much cooler. To maintain energy balance, the surface must become extremely hot. The result is a surface temperature near 460 degrees Celsius. Mars provides the opposite example. Its atmosphere is also mostly carbon dioxide, but it is extremely thin. Surface pressure on Mars is less than 1% of Earth's. There are far fewer molecules available to absorb infrared radiation. Outgoing heat escapes much more directly into space. Although carbon dioxide is present, the low density of the atmosphere limits its ability to create a strong greenhouse effect. Mars receives less sunlight than Earth because it is farther from the sun, but its thin atmosphere amplifies the cooling effect. Nighttime temperatures on Mars can fall below -100 degrees Celsius, even near the equator. Earth sits between these extremes. Its atmosphere is not thick enough to trap heat in a runaway way like Venus. It is not thin enough to allow rapid heat loss like Mars. Surface pressure at sea level averages about 101 kilopascals, providing enough density for greenhouse gases to interact frequently with infrared radiation, but not so much that radiation becomes permanently trapped. The layering also matters. The lowest layer, the troposphere, contains most of the water vapor and weather systems. It is here that clouds form, and convection circulates heat upward. Above it lies the stratosphere, where ozone absorbs ultraviolet radiation. Each layer has different temperature gradients and energy interactions. Together, they create a structured pathway for radiation to move outward gradually rather than abruptly. Gravity plays a quiet role in all of this. Earth's mass is sufficient to hold onto a stable atmosphere over billions of years. Smaller planets lose their atmospheres more easily, especially if they lack magnetic fields to shield them from solar wind. Without enough gravity, gas molecules can escape into space over time. Thickness, pressure, composition, and gravity all combine to determine how effectively a planet retains heat. You can imagine 3 spheres side by side, one wrapped in a heavy, dense blanket of gas, one almost bare, exposed directly to space, one covered in a moderate, balanced layer. The first overheats, the second freezes, the third stabilizes. Earth does not get too cold because its atmosphere has the right density to slow infrared escape without sealing it in completely. Molecules are close enough together to interact frequently with outgoing radiation, yet sparse enough to allow energy to leave steadily. A planet wrapped in too little gas cools rapidly. A planet wrapped in too much gas overheats. Earth's atmosphere rests in the middle, thick enough to hold warmth, thin enough to let excess energy radiate outward. And within that balanced thickness, energy flows continuously between surface and sky, upward and outward, in a steady exchange that prevents the deep freeze of open space. Mars is often called Earth's neighbor. It orbits the same sun. It rotates in a similar rhythm, completing one full spin in about 24 hours and 37 minutes. It has seasons caused by an axial tilt not far from Earth's. From a distance, it even shows polar caps that grow and shrink with the seasons, and yet its surface is far colder. On average, Mars sits at about -60 degrees Celsius. Near the equator, on a warm afternoon, temperatures can briefly rise above freezing. But at night, even in equatorial regions, they can plunge below -80 degrees. Near the poles, winter temperatures drop far lower still. Why does Mars get so cold? Part of the answer lies in distance. Mars orbits at an average of about 1.52 astronomical units from the Sun, compared to Earth's 1 astronomical unit. Because sunlight spreads out with distance, the solar energy reaching Mars is weaker. On average, Mars receives only about 43% of the solar energy that Earth does. Less energy arrives. So, less energy is available to warm the surface. But distance alone does not explain everything. If Mars had a thick atmosphere like Venus, it could still be warm despite receiving less sunlight. What matters equally is how energy is retained. Mars has an atmosphere composed mostly of carbon dioxide, similar in composition to Venus, but its atmosphere is extremely thin. Surface pressure on Mars averages about 6 millibars, compared to Earth's 1,013 millibars. That is less than 1% of Earth's surface pressure. There are far fewer molecules available to absorb outgoing infrared radiation. So when the Martian surface absorbs sunlight during the day and warms, it begins radiating infrared energy upward. With little atmospheric density to intercept that radiation, much of it escapes directly into space. Cooling happens quickly. The thin atmosphere also means there is limited heat redistribution. On Earth, winds and weather systems move warmth from equatorial regions toward the poles. On Mars, air circulation exists, but the low density limits how much heat can be transported. Local temperature differences can be dramatic. There is another difference that unfolds more slowly over time. Mars no longer has a global magnetic field like Earth's. Billions of years ago, it likely did. But as its internal heat declined and its core dynamics changed, the magnetic field weakened and disappeared. Without that protective field, the solar wind, a steady stream of charged particles flowing outward from the Sun, gradually stripped away much of Mars's atmosphere. NASA's MAVEN spacecraft has measured this process directly, observing how solar particles interact with the upper atmosphere and carry away gas molecules into space. Over millions and billions of years, the thinning atmosphere reduced Mars's greenhouse effect further. The planet became more exposed. Less atmosphere means less pressure, less absorption, and less delay in heat escape. Mars does not lack greenhouse gases entirely. Carbon dioxide is present in high percentage terms, but percentage is not the same as total mass. The total number of molecules matters. With so little atmospheric density, the greenhouse effect is weak. You can imagine sunlight striking the Martian surface, warming red dust and rock. Then picture infrared radiation rising upward. Instead of passing through layers of interacting molecules, it moves through a sparse medium and escapes quickly into space. Night falls, and the warmth drains away. Mars freezes not because cold invades it, but because heat leaves it too easily. Earth does not get too cold because it retained its atmosphere. Gravity held the gases close. A magnetic field shielded them from solar stripping. Oceans formed and water vapor contributed to greenhouse warming. The system remained thick enough to slow energy loss. Mars shows what happens when a planet is smaller, farther from the Sun, and wrapped in too little air. It receives less warmth. It cannot hold what it receives. And so, its surface rests in a colder balance, where radiation escapes with little resistance, and nighttime brings deep, immediate cooling beneath a thin pink sky. If Mars shows us what happens when a planet cannot hold on to its heat, Venus shows us what happens when a planet holds too much. At first glance, Venus and Earth seem similar. They are close in size. Venus is only slightly smaller than Earth in diameter and mass. Their compositions are comparable, both made primarily of silicate rock with metallic cores. They formed in the same region of the early solar system, under similar initial conditions. But today, Venus is nothing like Earth in temperature. Its average surface temperature is about 460 degrees Celsius. That is hot enough to melt lead. And unlike Earth, where temperatures vary between night and day, Venus remains extremely hot everywhere, all the time. The reason is not simply proximity to the Sun. Venus orbits at about 0.72 astronomical units from the Sun. It receives roughly twice the solar energy Earth does. That increased input certainly contributes to warming. But distance alone cannot explain the magnitude of the temperature difference. The key is atmospheric thickness and composition. Venus has an atmosphere composed of about 96% carbon dioxide. Surface pressure is around 92 times that of Earth. The atmosphere is so dense that standing on the surface would feel like being nearly 1 kilometer underwater on Earth in terms of pressure. In such a thick atmosphere, outgoing infrared radiation encounters layer after layer of absorbing molecules. When the surface of Venus absorbs sunlight and warms, it emits infrared radiation upward. Carbon dioxide molecules absorb that radiation efficiently. They re-emit it in all directions. But because the atmosphere is so thick, the radiation may be absorbed and re-emitted many times before finally reaching altitudes thin enough for it to escape into space. The effective radiating layer, the altitude from which energy can leave the planet, is very high in the atmosphere, where temperatures are far lower than at the surface. To maintain energy balance with incoming sunlight, the surface must become hot enough that even the upper atmosphere emits sufficient radiation to match the solar input. So the lower layers heat dramatically. This process is known as a runaway greenhouse effect. On early Venus, it is likely that liquid water once existed. As the planet warmed due to stronger sunlight and initial greenhouse gases, more water evaporated into the atmosphere. Water vapor itself is a powerful greenhouse gas. Increased water vapor amplified the warming, leading to more evaporation, which led to more warming still. Eventually, oceans may have completely evaporated. Ultraviolet radiation from the sun broke apart water molecules in the upper atmosphere. Hydrogen escaped into space. Oxygen reacted with surface materials. Without oceans to regulate carbon dioxide through weathering and carbon cycles, CO2 accumulated unchecked. The system shifted into a new equilibrium. Today, thick clouds of sulfuric acid surround Venus, reflecting much of the incoming sunlight. In fact, Venus has a higher albedo than Earth, reflecting about 75% of incoming solar radiation. Yet despite reflecting more sunlight than Earth, its surface remains vastly hotter because the outgoing infrared radiation is trapped so effectively. Venus does not cool easily at night because its rotation is extremely slow. One Venusian day lasts about 243 Earth days. But even that slow rotation is secondary to atmospheric density. The thick blanket of gas redistributes heat so efficiently that temperature differences between day and night are small compared to Mars. Venus shows that an atmosphere can become too effective at retaining heat. Earth sits between these extremes. Our atmosphere contains carbon dioxide, but at concentrations far lower than Venus. Our oceans absorb and dissolve CO2. Plate tectonics recycle carbon into rocks over millions of years. Water moderates temperature swings. The greenhouse effect operates, but it does not escalate uncontrollably. When we ask why Earth does not get too cold, we must also recognize why it does not overheat. The answer lies not in a single factor, but in a balance. Mars cannot hold heat. Venus cannot release it easily. Earth does both. It absorbs sunlight. It radiates infrared energy outward. Its atmosphere slows that radiation just enough to maintain temperate conditions without pushing into extremes. Venus stands as a reminder that atmospheric thickness and greenhouse strength can shift a planet into a very different thermal state. The difference between frozen and molten can emerge from how layers of gas interact with invisible radiation, flowing steadily upward into space. Given how similar Earth and Venus are in size and composition, it is reasonable to ask a deeper question. Why did Earth not follow the same path? Both planets formed from similar building blocks. Both likely began with volcanic outgassing, releasing carbon dioxide, water vapor, and other gases into their early atmospheres. Both received intense solar radiation during the young sun's more active phases. And yet, one planet stabilized with liquid oceans and moderate temperatures, while the other shifted into a runaway greenhouse state. The difference begins with distance. Earth orbits at a position where solar energy is strong enough to keep water liquid, but not so intense that evaporation becomes uncontrollable. Venus, closer to the Sun, received roughly twice as much solar energy from the start. That additional energy meant higher surface temperatures early in its history. Higher temperatures meant more evaporation. More evaporation meant more water vapor in the atmosphere. Water vapor is a powerful greenhouse gas. As water vapor increased on Venus, it amplified warming further. This is a feedback loop. A small increase in temperature causes more evaporation, which increases greenhouse trapping, which raises temperature again. If the initial energy input is strong enough, the loop can continue until all surface water evaporates. On Earth, early temperatures likely allowed water vapor to condense back into liquid form as the planet cooled. Clouds formed. Rain fell. Oceans accumulated. Liquid water became stable at the surface. And liquid water changes everything. On Earth, carbon dioxide does not simply accumulate in the atmosphere indefinitely. It dissolves in rainwater, forming weak carbonic acid. That acidic water reacts with silicate rocks on the surface in a process known as chemical weathering. Over long periods, this weathering pulls carbon dioxide out of the atmosphere and locks it into carbonate minerals. Rivers carry dissolved carbon to the oceans, where marine organisms incorporate it into shells and sediments. Plate tectonics then moves those carbon-bearing rocks into Earth's interior. Volcanic activity later releases some carbon dioxide back into the atmosphere. This creates a long-term carbon cycle operating over millions of years. It is a slow feedback system. If atmospheric carbon dioxide increases and warming begins, weathering rates rise because warmer temperatures and increased rainfall accelerate chemical reactions. More CO2 is removed. Cooling follows. If temperatures fall, weathering slows. Carbon dioxide accumulates from volcanic emissions. Warming resumes. This negative feedback stabilizes Earth's climate over geological time. Venus appears not to have developed this kind of long-term regulation. Without stable liquid oceans, weathering could not operate effectively. Carbon dioxide remained in the atmosphere. Volcanic outgassing added more. The greenhouse effect intensified. Another difference may lie in planetary rotation and cloud dynamics. Some climate models suggest that slowly rotating planets like Venus may form thick cloud decks at certain altitudes. These clouds reflect sunlight, but also trap infrared radiation below. The balance of reflection and trapping on Venus appears to favor warming at the surface, despite high reflectivity. Earth's faster rotation produces more dynamic weather systems. Clouds form and dissipate rapidly. They both reflect sunlight during the day and trap infrared radiation at night. The balance remains moderated rather than extreme. Earth's magnetic field may also have played a quiet role. By shielding the atmosphere from direct solar wind erosion, it helped preserve the gases necessary for long-term stability. Venus lacks a strong intrinsic magnetic field, leaving its upper atmosphere more exposed to solar stripping processes. Small differences in early conditions led to diverging paths, slightly farther distance. Liquid water that remains stable. An active carbon cycle tied to plate tectonics. A magnetic field that preserved atmospheric mass. Together, these factors prevented the feedback loop that drove Venus toward runaway warming. Earth does not get too cold, and it does not overheat uncontrollably, because its energy balance is coupled to slow regulatory systems. Incoming sunlight warms the surface. Greenhouse gases slow heat loss. Liquid water moderates temperature swings. Chemical weathering adjusts carbon dioxide levels. Plate tectonics recycle carbon over immense spans of time. The planet responds to change, not instantly, but persistently. Where Venus crossed a threshold and shifted into a new equilibrium of extreme heat, Earth remained within a narrower band. A difference of orbital distance measured in fractions of an astronomical unit, combined with feedbacks measured in molecular interactions and geological cycles, determined the fate of two neighboring worlds. And in that difference, Earth retained oceans instead of steam, clouds instead of acid haze, and a surface that did not freeze into silence or burn into permanence. There is another difference between Earth and the Moon that is easy to overlook because it feels ordinary. Earth turns quickly. One full rotation takes about 24 hours. That steady spin carries continents and oceans into sunlight and then back into darkness in a continuous rhythm. Sunrise moves across the surface like a slow wave. Noon passes. Evening arrives. Night cools the land. Then morning begins again. Sunlight is always moving. Because of this rotation, no region remains exposed to the sun for weeks at a time. There is no prolonged baking period like the one experienced on the Moon, where a single location can face the sun continuously for nearly 14 Earth days. On Earth, even at the equator, the longest daylight period lasts only about 12 hours. At higher latitudes in summer, it may stretch longer, but never for weeks without interruption. This matters for temperature. When sunlight strikes the surface, it begins warming the ground and water beneath it. Molecular motion increases. Infrared radiation rises upward, but the heating window is limited. Before the surface can reach extreme temperatures, the planet has already rotated. the angle of sunlight decreases. Eventually, night arrives. Cooling begins. But night, too, is limited. Darkness lasts hours, not weeks. The surface radiates heat upward. But before it can drop to deep extremes, sunrise returns and warming resumes. This alternating pattern prevents runaway daily heating or cooling. On the Moon, where rotation is slow and the atmosphere absent, surface temperatures have time to rise and fall dramatically. During its long day, solar energy accumulates without interruption. During its long night, heat radiates away for extended periods with nothing to slow the loss. Earth's faster rotation distributes solar input more evenly across time. You can picture a line of sunlight sweeping across the planet's curve. The terminator, the boundary between day and night, advances steadily. No location remains fixed in light or darkness for long. Rotation also interacts with the atmosphere in another way. As the surface warms unevenly, more at the equator, less at the poles, differences in temperature drive air circulation. Warm air rises, cooler air sinks, winds form. These movements redistribute heat horizontally. Energy absorbed in one region can be carried to another. The rotation of Earth shapes these patterns through the Coriolis effect, creating trade winds, jet streams, and large-scale weather systems. Without rotation, atmospheric circulation would look very different. With rotation, the planet avoids stagnant heating zones. Another important detail lies in thermal inertia. Land surfaces heat quickly during the day and cool quickly at night. But the atmosphere and oceans respond more slowly. As Earth rotates, sunlight strikes the oceans as well as the land. Water absorbs energy more gradually. When night falls, the oceans release stored heat slowly back into the air. This moderates nighttime cooling. Because rotation is regular and continuous, the heating cycle is predictable. The system adjusts to a rhythm. Daily temperature swings exist, but they remain within bounds set by atmospheric and oceanic moderation. If Earth rotated much more slowly, daytime heating would intensify. If it rotated much faster, temperature gradients between day and night would shrink further. The 24-hour period sits in a range that supports moderate fluctuations without extreme buildup. Earth does not get too cold at night because night does not last long enough for unchecked radiative cooling to drive temperatures towards space-like conditions. The greenhouse effect continues operating after sunset. The atmosphere continues absorbing and re-emitting infrared radiation. Oceans continue releasing stored warmth. Rotation ensures that energy input and output remain dynamic, rather than static. Sunlight moves, shadows shift. Heat rises and falls in cycles that prevent prolonged exposure to either extreme. A turning planet experiences warmth and cooling in steady alternation, never pausing long enough for the deep freeze of space to claim the surface. If rotation shapes the rhythm of heating and cooling, the oceans shape the depth of it. Water behaves differently from rock or air when it comes to heat. It takes a large amount of energy to raise the temperature of water even a single degree. This property is known as high heat capacity. Compared to most materials found on land, water can absorb far more energy without changing temperature quickly. This makes the oceans enormous thermal reservoirs. When sunlight strikes the surface of the ocean, much of that energy does not immediately translate into rapid temperature increases. Instead, the energy spreads through layers of water. Surface currents move it horizontally. Vertical mixing distributes it downward. The upper layers warm gradually rather than sharply. During the day, the ocean absorbs solar radiation steadily. At night, it does not cool instantly. Because water holds energy so effectively, it releases stored heat slowly over time. Even after sunset, warmth continues to rise from the ocean surface into the atmosphere. This moderates nighttime temperature drops, especially in coastal regions. If you compare inland deserts to coastal cities at similar latitudes, the difference is clear. Deserts can swing from very hot days to cold nights because dry land and sand heat and cool quickly. Coastal areas experience smaller daily temperature changes because the nearby ocean buffers the shifts. The ocean is not only a passive storage system, it moves. Large-scale currents, such as the Gulf Stream in the Atlantic, transport warm water from tropical regions toward higher latitudes. This movement redistributes solar energy around the planet. Western Europe, for example, remains far warmer in winter than other regions at similar latitudes, partly because of oceanic heat transport. Without oceans, Earth's climate would look very different. Land surfaces alone would heat rapidly under sunlight and cool rapidly at night. Temperature extremes would become more pronounced. The daily and seasonal cycles would feel sharper. Water's high heat capacity smooths those transitions. There is also depth to consider. The oceans are not shallow pools. They average nearly 4 kilometers in depth. Beneath the surface lies an immense volume of water capable of storing vast quantities of thermal energy. Even though sunlight penetrates only the upper layers directly, mixing processes carry energy downward. The deep ocean becomes a long-term storage system, absorbing excess warmth during warmer periods and releasing it gradually during cooler ones. This does not eliminate climate change or temperature variation, but it slows the pace at which changes occur. Another property of water contributes to stability. When water evaporates, it absorbs energy from its surroundings. This process is called latent heat absorption. During evaporation, energy is stored in water vapor without immediately raising temperature. Later, when water vapor condenses into clouds or precipitation, that stored energy is released back into the atmosphere. This transfer of latent heat drives weather systems and further redistributes energy across the globe. In tropical regions, strong sunlight leads to evaporation. Moist air rises, carrying energy upward. Condensation releases that energy at higher altitudes. Air circulation then moves it elsewhere. The oceans feed this cycle continuously. Water also influences greenhouse strength. Warmer oceans release more water vapor into the atmosphere. Water vapor, as discussed earlier, is an effective greenhouse gas. This creates a feedback loop. When surface temperatures rise slightly, water vapor increases, strengthening the greenhouse effect and reducing cooling. When temperatures fall, water vapor decreases, allowing more infrared radiation to escape. The oceans are central to this feedback because they supply most of the atmospheric moisture. Without oceans, Earth would not only lack its largest heat reservoir, but also one of its most important greenhouse contributors. You can imagine Earth without oceans, a rocky surface exposed directly to sunlight and darkness, responding quickly and sharply to every change in energy input. Instead, our planet is covered by vast expanses of water that absorb, move, and release heat with patience. The oceans do not prevent cooling entirely. They do not trap warmth indefinitely, but they slow the transitions. They extend the time it takes for energy to leave the system. Earth does not get too cold because heat absorbed during the day does not vanish when night arrives. It lingers in the upper layers of the sea. It moves through currents. It returns to the air gradually. A rotating planet wrapped in air and covered in water experiences temperature not as abrupt swings, but as moderated cycles. And beneath the shifting clouds and moving winds, the oceans hold warmth quietly, releasing it in measured amounts that keep the surface far from the frozen silence of space. Not all incoming sunlight stays. Before solar energy can warm the ground or the ocean, some of it is turned away. It is reflected back into space without ever being absorbed. This reflection plays a quiet but essential role in regulating Earth's temperature. The term for reflectivity is albedo. A surface with high albedo reflects a large fraction of incoming light. A surface with low albedo absorbs more. Fresh snow has a very high albedo, reflecting up to 80 or even 90% of sunlight. Thick clouds can also reflect significant portions of incoming radiation. Dark ocean water, by contrast, absorbs most of the light that reaches it. When sunlight encounters Earth, about 30% of it is reflected back into space. This reflection occurs at several levels. Some sunlight is scattered by molecules in the upper atmosphere. Tiny particles and aerosols reflect a small portion. Clouds reflect much more. From space, Earth's cloud tops appear bright white because they are sending light outward rather than absorbing it. Snowfields, glaciers, and polar ice sheets also contribute to planetary reflectivity. The remaining 70% of incoming solar radiation is absorbed by the atmosphere, land, and oceans. This balance between reflection and absorption sets the baseline for how much energy the planet must manage. If Earth reflected far less sunlight, more energy would be absorbed, and surface temperatures would rise until outgoing infrared radiation increased enough to restore equilibrium. If Earth reflected far more sunlight, less energy would be absorbed, and the planet would cool. Clouds sit at the center of this balance. During the day, clouds reduce surface heating by reflecting sunlight away. On a cloudy afternoon, temperatures tend to remain lower than on a clear day. Yet at night, those same clouds can trap outgoing infrared radiation, slowing cooling. The net effect of clouds depends on their altitude, thickness, and type. Low, thick clouds tend to reflect more sunlight than they trap infrared radiation, producing a cooling influence overall. High, thin clouds, such as cirrus, reflect less sunlight, but can trap outgoing heat more effectively, contributing to warming. This dual role makes clouds both mirrors and insulators. Ice and snow provide another stabilizing mechanism. When temperatures fall and snow expands, albedo increases. More sunlight is reflected, promoting further cooling. This is a positive feedback loop. During ice ages, expanded ice sheets reflected more solar energy, reinforcing colder conditions. Conversely, when ice melts and exposes darker land or ocean beneath, albedo decreases. More sunlight is absorbed, promoting warming. This feedback amplifies temperature shifts, but does not initiate them alone. Oceans have low albedo compared to ice. Dark water absorbs most of the sunlight that reaches it. This absorption supports the heat storage role discussed earlier. Yet, if too much ice disappears, reduction in reflectivity can accelerate warming trends. Albedo also varies with vegetation and land cover. Forests absorb more sunlight than deserts. Urban surfaces absorb differently than fields. These variations shape local and regional climates. From space, Earth's brightness changes with cloud cover and seasonal snow. Satellites monitor these changes carefully because even small shifts in reflectivity alter the global energy budget. The balance between energy in and energy out begins not only with greenhouse gases, but also with how much sunlight is allowed to enter the system at all. Imagine two identical planets. One covered mostly in bright ice, reflecting much of its sunlight. The other covered mostly in dark ocean, absorbing it. Even if their atmospheres were the same, their surface temperatures would differ because of how much solar energy they retain. Earth's current balance reflects a mixture of surfaces: oceans, forests, deserts, ice caps, and a dynamic cloud system. The combination reflects enough sunlight to prevent overheating while absorbing enough to maintain warmth. Albedo works alongside the greenhouse effect. One governs how much energy arrives. The other governs how quickly it leaves. Together, they define the equilibrium temperature. Earth does not get too cold because it absorbs a sufficient fraction of sunlight to sustain warmth. It does not get too hot because a portion of that sunlight is reflected back into space before it can contribute to heating. Between reflection and absorption, between brightness and darkness, the planet maintains a careful accounting of energy. And that accounting unfolds constantly above us, in drifting clouds and shifting ice, in surfaces that either return light to the void or hold it briefly before releasing it again as invisible infrared glow. Earth is stable, but is not fixed. The planet has experienced long stretches of colder climate in its past. Ice sheets have expanded. Glaciers have advanced across continents. Sea levels have fallen as water became locked in ice. These periods are known as ice ages. An ice age does not mean the entire planet freezes solid. Even during the most recent glacial maximum, about 20,000 years ago, large areas near the equator remained ice-free. But global average temperatures were several degrees Celsius lower than today, and ice covered much of North America and Northern Europe. This tells us something important. Earth can get colder. The balance between incoming sunlight and outgoing radiation can shift enough to lower global temperatures for thousands of years. One major driver of these long-term shifts lies in orbital mechanics. Earth's orbit around the Sun is not perfectly constant. Over tens of thousands to hundreds of thousands of years, three subtle cycles alter how sunlight is distributed across the planet. The first is eccentricity, which describes the shape of Earth's orbit. Sometimes it is more circular. Sometimes it becomes slightly more elliptical. This changes the difference in solar energy received at different points in the year. The second is axial tilt, also called obliquity. Earth's tilt varies between about 22 and 24.5 degrees over a cycle of roughly 41,000 years. Greater tilt increases seasonal contrast. Less tilt softens seasons. The third is precession, a slow wobble in Earth's rotational axis that changes the timing of seasons relative to Earth's position in its orbit. These combined cycles are often referred to as Milankovitch cycles, named after the scientist who studied their climatic influence. Individually, the changes in solar input from these cycles are modest, but they alter how much sunlight reaches high latitudes during summer. When northern summers are cooler, winter snow may not melt completely. Ice accumulates gradually. Over thousands of years, this accumulation increases albedo, reflecting more sunlight and promoting further cooling. Feedback loops amplify the initial orbital shifts. As ice sheets expand, more sunlight is reflected. Oceans cool. Water vapor decreases. With less water vapor in the atmosphere, the greenhouse effect weakens slightly, allowing more infrared radiation to escape. Cooling deepens. Carbon dioxide levels have also varied during ice ages. As oceans cool, they can absorb more carbon dioxide from the atmosphere. Lower atmospheric CO2 reduces greenhouse warming, reinforcing cooler conditions. These processes unfold slowly. Ice sheets grow centimeter by centimeter over centuries. Temperatures shift gradually. Ocean currents adjust. Then, orbital configurations change again. Summers grow warmer in key regions. Ice begins to melt. Darker surfaces absorb more sunlight. Greenhouse gases increase as oceans release dissolved carbon dioxide. The planet warms. The most recent ice age ended about 11,700 years ago, marking the beginning of the current interglacial period, known as the Holocene. This history shows that Earth's temperature is not locked into a single value. It responds to subtle shifts in solar distribution and internal feedbacks. And yet, even during these colder phases, Earth did not become Mars-like. The atmosphere remained thick enough to prevent runaway freezing. The oceans did not vanish. Liquid water persisted beneath ice sheets and across much of the globe. Greenhouse gases remained present, even if reduced. The system shifted within bounds. Ice ages demonstrate that Earth can cool significantly when conditions align. But they also demonstrate resilience. The same feedbacks that allow cooling eventually contribute to warming when orbital patterns shift. Earth does not get too cold in a permanent sense, because its climate system contains balancing mechanisms. Orbital cycles alter energy distribution. Ice and albedo amplify changes. Greenhouse gases respond. Oceans absorb and release heat. Temperature rises and falls over geological time, but always in response to energy balance. Even in its coldest glacial states, Earth retained enough atmospheric insulation and solar input to prevent complete freezing. The planet breathes slowly through cycles of cooling and warming. Not fixed, not fragile, but responsive, adjusting over millennia to shifts in sunlight and feedback, never drifting into the deep, unbroken cold of open space. When we think about warmth on Earth, we usually look upward. The sun dominates the energy budget of the planet. Nearly all the energy that drives weather, ocean currents, and climate begins as sunlight arriving from 150 million kilometers away. But there is also warmth rising from below. Deep beneath the crust, far below oceans and continents, Earth's interior remains hot. The core temperature is estimated to be similar to the surface of the sun, reaching several thousand degrees Celsius. This heat is a remnant of planetary formation, an ongoing radioactive decay. When Earth formed more than 4 billion years ago, collisions between rocky bodies released enormous amounts of energy. Gravitational compression added more heat. Heavy elements sank toward the center, releasing further energy through friction. Much of that original heat remains trapped inside. In addition, radioactive elements such as uranium, thorium, and potassium undergo slow decay within the mantle and crust. As these atoms break apart over time, they release heat steadily. The process is gradual but persistent, contributing to the internal thermal reservoir. This internal energy moves outward very slowly. Heat travels from the core through the mantle by convection, where hotter material rises and cooler material sinks in cycles that can take millions of years. Eventually, some of that heat reaches the crust. Volcanoes, hydrothermal vents, and geothermal springs are visible expressions of this upward flow. On average, the geothermal heat flux at Earth's surface is about 0.1 watts per square meter. Compared to the roughly 240 watts per square meter of absorbed solar energy, this is small. Sunlight outweighs geothermal heat by more than 1,000 times in terms of influence on surface temperature. So internal heat does not prevent Earth from freezing on a daily basis. It does not significantly influence the greenhouse effect or the balance of incoming and outgoing radiation, but it matters in quieter ways. Internal heat drives plate tectonics. Without it, Earth's crust would not fracture into moving plates. Continents would not drift. Mountains would not rise. Volcanic outgassing would be minimal. And without volcanic outgassing, the atmosphere would look different. Over geological timescales, volcanoes release carbon dioxide into the atmosphere. That carbon dioxide contributes to the greenhouse effect. In turn, chemical weathering removes carbon dioxide, cycling it back into rocks. This balance between volcanic input and weathering removal forms part of the long-term carbon cycle discussed earlier. If Earth's interior cooled completely and tectonic activity ceased, carbon dioxide release from volcanoes would decline. Over millions of years, weathering could draw down atmospheric CO2 to very low levels. The greenhouse effect would weaken. Surface temperatures would gradually fall. So while geothermal heat does not warm your skin directly or shape today's weather, it sustains the geological engine that helps regulate atmospheric composition over deep time. There are also localized effects. In certain regions, geothermal activity warms groundwater. Iceland, for example, harnesses geothermal energy for heating and electricity. Hydrothermal vents on the ocean floor release heat into deep waters. Though minor compared to solar input, these sources contribute to ocean circulation patterns and chemical exchanges. The warmth rising from below is subtle. It does not glow visibly from the surface. It does not prevent night from cooling the land, but it keeps Earth internally active. A completely cold planet internally would be geologically quiet. Its atmosphere might gradually thin through lack of replenishment. Its magnetic field could weaken without convection in the outer core. Earth's interior heat also powers the geodynamo that generates the magnetic field. That magnetic field shields the atmosphere from solar wind stripping. In that indirect way, internal heat helps preserve the very gases that insulate the surface from freezing. So when we ask why Earth does not get too cold, the primary answer points to sunlight and atmospheric physics. But beneath that, a deeper warmth sustains the geological systems that stabilize the atmosphere over billions of years. From above, sunlight arrives steadily. From below, heat rises slowly. One dominates the surface temperature directly. The other maintains the machinery that supports long-term balance. Together, they create a planet that remains thermally alive, not only in the air we breathe and the oceans we cross, but in the slow, persistent warmth moving upward through stone, keeping Earth dynamic rather than silent. There is one more quiet protector that rarely enters everyday conversation about temperature. It is invisible. It does not trap heat directly. But without it, the atmosphere itself might not have endured long enough to do its work. Earth has a magnetic field, generated deep within the outer core, where molten iron moves in slow convective currents. This magnetic field extends outward into space. It forms a vast protective region called the magnetosphere, stretching tens of thousands of kilometers toward the sun and trailing even farther behind the planet like a long, invisible tail. The sun does not only emit light and heat, it also emits a continuous stream of charged particles known as the solar wind. These particles travel at high speeds, carrying energy and magnetic fields of their own. When they encounter a planet, they can interact with its upper atmosphere. If a planet lacks a strong magnetic field, the solar wind can gradually strip away atmospheric gases. Charged particles transfer energy to atoms in the upper atmosphere, giving some of them enough velocity to escape the planet's gravitational pull. This process is slow on human timescales, but over millions and billions of years, it can significantly thin an atmosphere. Mars offers an example. Evidence suggests that early Mars once had a thicker atmosphere and liquid water on its surface. But as its internal heat declined, the dynamo in its core weakened. Its global magnetic field faded. Without that shield, the solar wind interacted more directly with the Martian atmosphere. Over time, much of the atmosphere was lost to space. As the atmosphere thinned, the greenhouse effect weakened. Heat escaped more easily. Surface temperatures fell. Earth retained its magnetic field because its interior remained hot and dynamic. Convection in the liquid outer core continues to generate electrical currents, and those currents sustain the magnetic field. The magnetosphere deflects most of the solar wind around the planet rather than allowing it to impact the upper atmosphere directly. This does not mean atmospheric loss never occurs on Earth. Light gases such as hydrogen can escape into space from the upper atmosphere, but the bulk of the atmosphere remains protected from direct stripping. The magnetic field does not warm the surface. It does not reflect sunlight. It does not absorb infrared radiation. Its role is more foundational. It helps preserve the atmosphere that performs those functions. Without sufficient atmospheric mass, the greenhouse effect would weaken. Pressure would drop. Water vapor would decline. Surface temperatures would respond. Over long stretches of time, retaining an atmosphere is essential for maintaining thermal stability. The magnetosphere also shields the surface from much of the sun's high-energy radiation. While the ozone layer absorbs ultraviolet radiation within the atmosphere, the magnetic field deflects many charged particles before they reach the upper layers at all. This protection helps prevent direct atmospheric erosion and reduces radiation reaching the surface. You can imagine Earth wrapped not only in air, but also in an invisible magnetic bubble. Solar particles approach. The magnetic field guides many of them around the planet. Some spiral toward the poles, producing auroras, shimmering lights in the night sky. But the majority are diverted. The system works quietly. We rarely feel it, but its long-term effect is profound. A planet without a magnetic field may gradually lose atmospheric density. A thinner atmosphere traps less heat. Radiative cooling becomes more efficient. Over geological timescales, such changes alter surface temperature significantly. Earth does not get too cold in part because it kept the envelope of gas that moderates heat exchange. And it kept that envelope because gravity held it. Internal heat sustained tectonics and atmospheric replenishment, and the magnetic field shielded it from being stripped away. Distance from the sun set initial conditions. Atmospheric composition shaped radiation balance. Oceans stored heat. Rotation distributed sunlight. Internal warmth sustained geology. And the magnetic field preserved the atmosphere across billions of years. Each factor alone would not be enough. Together, they form layers of stability. Above us, infrared radiation rises steadily toward space. Around us, air molecules absorb and re-emit that radiation. Beneath us, heat circulates in stone. And beyond us, an invisible magnetic boundary deflects solar wind, ensuring the atmosphere remains thick enough to continue its quiet work. Earth does not resist cold through a single shield. It remains temperate because multiple systems cooperate across scales. From atomic vibrations in greenhouse gases to molten iron moving thousands of kilometers below the crust, all maintaining the conditions that keep the planet from slipping into the frozen stillness of open space. It can be tempting to imagine Earth's temperature as a fixed setting, as if somewhere, quietly, the planet has settled on a number and remains there without change. But energy balance is not static. It is ongoing. At every moment, sunlight is arriving. At every moment, infrared radiation is leaving. The two flows are nearly equal when averaged over time, but they are never perfectly identical at every instant. Small imbalances occur constantly. A volcanic eruption can inject particles into the upper atmosphere, reflecting more sunlight temporarily and cooling the surface slightly. Changes in ocean circulation can redistribute stored heat, altering regional temperatures. Variations in greenhouse gas concentrations adjust how efficiently infrared radiation escapes. When incoming energy exceeds outgoing energy even by a small fraction, the planet warms until balance is restored. When outgoing energy exceeds incoming energy, cooling continues until equilibrium returns. Because of the Stefan-Boltzmann relationship, where radiation increases with the fourth power of temperature, the system has a built-in stabilizing feature. As temperature rises, outgoing radiation increases more rapidly. As temperature falls, outgoing radiation decreases. This tendency pushes the system back toward balance, but feedbacks complicate the picture. Water vapor increases as temperature rises, strengthening the greenhouse effect. Ice melts as temperatures increase, lowering albedo and allowing more solar absorption. Conversely, cooling can increase ice cover and reduce water vapor, amplifying cold conditions. These feedbacks determine climate sensitivity, the degree to which temperature responds to a change in energy balance. If the atmosphere were less responsive, small energy shifts would produce large temperature swings. If it were overly responsive in the opposite direction, temperature would snap back instantly without variation. Earth sits somewhere between these extremes. The adjustments unfold over different timescales. Daily changes are driven by rotation. Seasonal shifts arise from axial tilt. Glacial cycles operate over tens of thousands of years. Carbon cycling and tectonic processes span millions of years. All of these influence how the planet responds to energy imbalances. Energy balance is not a single equation solved once in the distant past. It is recalculated continuously. Satellites today measure Earth's radiation budget with remarkable precision. They track how much solar energy enters the top of the atmosphere and how much infrared radiation leaves. Even small differences, measured in fractions of a watt per square meter, matter over time. If slightly more energy enters than leaves, the excess accumulates, mostly in the oceans. If slightly more leaves than enters, the planet cools gradually. These imbalances do not produce immediate dramatic changes. The oceans absorb excess energy slowly. Ice responds over decades. The atmosphere adjusts rapidly, but the entire system evolves over layered timescales. Earth does not get too cold because outgoing energy is balanced against incoming sunlight, and because feedbacks adjust when that balance shifts. If the planet cools slightly, outgoing infrared radiation decreases, and greenhouse gases and water vapor respond. If it warms slightly, radiation increases, pushing energy outward more efficiently. The system is dynamic, not rigid. You can imagine a scale that never stops moving. On one side, sunlight. On the other, infrared glow. The scale tips slightly back and forth, but over time, it hovers near balance. That hovering state is what keeps the planet temperate. Not perfection, not immobility, but constant adjustment. A planet wrapped in layers of interacting processes, responding to tiny shifts in energy with subtle changes in temperature, always seeking equilibrium without ever becoming frozen in place. And in that ongoing recalculation, Earth remains far from the deep, empty cold that surrounds it. When the sun sets, it can feel like warmth disappears, light fades, shadows stretch, air cools. It might seem intuitive that once sunlight stops, the surface should begin freezing rapidly, especially given that space itself is often described as extremely cold. But nighttime is not space. When darkness falls on Earth, the surface does begin to lose heat. Infrared radiation continues rising upward from soil, pavement, forests, and oceans. Molecules vibrate less as energy leaves. Temperatures drop gradually, but cooling is moderated at every step. First, the atmosphere remains in place. Even after sunset, greenhouse gases continue absorbing and re-emitting infrared radiation. Outgoing heat does not pass unimpeded into the vacuum. Water vapor, carbon dioxide, and other gases intercept portions of the upward radiation and send some of it back toward the surface. The process does not stop simply because visible sunlight is gone. Infrared exchange continues through the night. Second, the oceans release stored heat. Throughout the day, large bodies of water absorb solar energy. That energy did not raise their temperature dramatically because of water's high heat capacity. Now, during nighttime, that stored warmth begins moving back into the atmosphere. Coastal regions often experience milder nighttime temperatures because nearby oceans buffer cooling. Even inland lakes can have similar localized effects. Third, the ground itself stores heat. Soil, rock, and buildings absorb energy during daylight hours. They do not lose it instantly at sunset. Instead, they cool over several hours. This is why the coldest time of night often occurs just before sunrise, not immediately after dusk. Cooling accumulates gradually. Cloud cover plays a significant role as well. On clear nights, infrared radiation can escape more efficiently through atmospheric windows, allowing temperatures to drop more sharply. On cloudy nights, clouds absorb outgoing infrared radiation and re-emit some of it downward. This reduces the rate of cooling. Meteorologists observe this effect routinely. A cloudy winter night may remain warmer than a clear one, even without any sunlight. The atmosphere also redistributes heat horizontally. Wind can carry warmth from one region to another. Air masses mix. Temperature differences are smoothed out by circulation. Even at night, these processes continue. Contrast this with the moon. When night falls on the lunar surface, there is no air to absorb and re-emit radiation. No oceans release stored heat. No clouds reflect or redirect infrared energy. The ground radiates heat directly into space without delay. Cooling becomes severe. Earth's nighttime is moderated by layers of interaction. The surface cools. The atmosphere responds. The oceans release energy. Clouds adjust the rate of radiation escape. Because of these processes, temperatures rarely approach the extremes seen in airless environments. Even in deserts, where cooling can be dramatic after sunset, temperatures fall within bounds set by atmospheric insulation. And in humid regions, where water vapor concentrations are higher, nighttime cooling is further softened. Night is not the absence of physics. It is the continuation of energy exchange without visible light. The same infrared glow that radiates from Earth during the day continues in darkness. Satellites detect this radiation equally at night. The planet does not turn cold instantly when sunlight disappears, because outgoing energy is moderated by atmospheric absorption and surface heat storage. So when we return to the original question, why doesn't Earth get too cold? Nighttime provides a simple example. If Earth were exposed directly to space without air or water, sunset would bring rapid freezing. Instead, the cooling unfolds gradually. The atmosphere slows the loss. The oceans release stored warmth. Clouds reshape the radiation pathway. Morning returns before the system can drift far from equilibrium. Sunlight rises again. Heating resumes. The cycle repeats. Earth does not sit in constant daylight, yet it also does not plunge into space like cold each night. The difference lies not in distance from the vacuum, but in the layered physics surrounding the surface. Darkness is not the same as emptiness, and night on Earth remains part of a balanced exchange, not a descent into the frozen stillness beyond the atmosphere. There is a narrow range of temperatures in which liquid water can exist. At standard atmospheric pressure, water freezes at 0 degrees Celsius and boils at 100 degrees Celsius. Between those 2 points lies the familiar range of rivers, rain, oceans, and clouds. Outside that range, water becomes ice or vapor. The existence of long-lasting liquid water on Earth is not accidental. It depends on pressure, temperature, and energy balance working together. Water has what is known as a triple point, a specific combination of temperature and pressure at which solid, liquid, and vapor phases can coexist. For water, that occurs at about 0.01 degrees Celsius and 611 pascals of pressure. If atmospheric pressure falls below that level, liquid water cannot remain stable. It transitions directly between ice and vapor through sublimation. Mars provides an example. Because its atmospheric pressure is so low, near or below the triple point of water in many regions, liquid water is unstable. Ice can sublimate directly into vapor without becoming liquid first. This contributes to the difficulty of maintaining surface oceans on Mars today. Earth's atmospheric pressure is far above the triple point threshold. That pressure allows liquid water to remain stable across a wide temperature range. Combined with moderate solar input and greenhouse insulation, this creates conditions where oceans can persist for billions of years. But the margin is not infinite. If Earth were slightly closer to the Sun, increased solar energy might have pushed average temperatures higher. More water would evaporate. Water vapor would amplify the greenhouse effect. If evaporation outpaced condensation for extended periods, the system could shift toward a much warmer equilibrium. If Earth were slightly farther from the Sun, reduced solar input might have allowed ice to expand more easily. Increased reflectivity could have reinforced cooling. With lower temperatures, water vapor would decrease, weakening the greenhouse effect and allowing further heat escape. These differences need not be dramatic. Even small changes in solar distance alter the amount of incoming energy significantly, because radiation decreases with the square of distance. Move a planet 10% farther from the Sun, and it receives roughly 20% less energy. That change alone could shift equilibrium temperatures substantially. Astronomers refer to the range of orbital distances around a star where liquid water can exist on a planet's surface as the habitable zone. It is not a sharp boundary, but rather a band where energy input and atmospheric conditions might allow water to remain liquid over long timescales. Earth sits within this band. not at its center by exact measurement, but within a range that permits oceans to persist. Venus lies closer to the inner edge of the Sun's habitable zone. Mars lies near or beyond the outer edge, but habitability depends not only on distance. Atmospheric thickness, greenhouse strength, rotation, and feedback systems all shape final temperature. The narrow window for liquid water depends on the interplay of these factors. Earth's gravity holds enough atmosphere to maintain pressure. Greenhouse gases slow infrared escape enough to prevent freezing. Albedo reflects enough sunlight to prevent overheating. Rotation distributes heat. Oceans store and release energy. Together, these systems keep global average temperature within the bounds where water remains liquid across most of the surface. If any one factor shifted dramatically, the balance could change. Remove the greenhouse effect entirely, and average temperature would drop below freezing globally, increase atmospheric density drastically, and surface temperatures could rise far beyond boiling at current pressures. Reduce solar input significantly, and ice could dominate. Increase it significantly, and evaporation could intensify. The window is not infinitely wide, but it is maintained by ongoing physics. Earth does not remain temperate because of chance alone. It remains temperate because its position, atmosphere, rotation, and internal processes combine to hold temperature within a band that supports liquid water. A small orbital difference, a thinner atmosphere, or weaker greenhouse absorption could have pushed the planet toward a colder equilibrium. Instead, sunlight arrives in measured amounts. Infrared radiation leaves in moderated streams. Pressure remains high enough for liquid stability. And within that narrow window, oceans endure, clouds form, and rivers flow rather than freeze or vanish into vapor. When you step back and look at the full picture, no single explanation is enough. Earth does not avoid deep cold because of one protective shield or one fortunate detail. It remains temperate because multiple systems operate together, quietly and continuously. Start with distance. Earth orbits at a range where sunlight is strong but not overwhelming. The sun delivers a steady stream of energy, enough to warm oceans but not so intense as to guarantee runaway heating. That incoming light sets the baseline. Then consider rotation. Every 24 hours, the planet turns. Sunlight sweeps across continents and seas. No region bakes for weeks at a time. No region freezes in darkness for extended cycles. Heating and cooling alternate predictably. The rotation also shapes wind patterns that redistribute warmth across latitudes. Add the atmosphere. Nitrogen and oxygen provide bulk and pressure. Water vapor, carbon dioxide, methane, and other greenhouse gases absorb and re-emit infrared radiation. Outgoing heat does not escape instantly. It lingers briefly, redirected and moderated before leaving the system. The atmosphere is thick enough to matter, thin enough to allow balance. Layer onto that the oceans. They absorb solar energy slowly and release it slowly. They move heat from equator to poles through currents. They supply water vapor that strengthens the greenhouse effect when temperatures rise and reduces it when temperatures fall. They buffer daily and seasonal swings. Include clouds and albedo. Clouds reflect sunlight during the day and trap infrared radiation at night. Ice sheets reflect more light when they expand. dark oceans absorb more when ice retreats. Reflection and absorption adjust how much energy enters the system before the greenhouse effect even acts. Consider internal heat. Deep below the crust, radioactive decay and residual formation energy sustain tectonic movement. Volcanic activity releases carbon dioxide. Plate tectonics recycle carbon through weathering and subduction. Over millions of years, this cycle regulates atmospheric composition, and surrounding it all, the magnetic field. Generated in the molten outer core, it deflects solar wind and helps preserve the atmosphere over billions of years. Without it, the very gases that moderate heat could have been eroded more rapidly. Each element interacts. Rotation affects cloud formation. Oceans influence atmospheric moisture. Greenhouse gases shape temperature, which shapes ice cover, which shapes albedo. Internal geology influences atmospheric carbon levels. The magnetic field preserves atmospheric mass, allowing greenhouse processes to continue. None of these systems operate in isolation. You can imagine Earth as a sphere wrapped in layers of physics. Sunlight enters. Some is reflected. Some is absorbed. The surface warms and emits infrared radiation. Greenhouse gases reshape that radiation's path. Oceans store and move energy. Winds circulate warmth. Clouds adjust reflection and trapping. Geological cycles regulate atmospheric composition. The magnetosphere shields the envelope that makes all of this possible. Energy flows through this structure continuously. At any given moment, trillions of infrared photons are rising upward. Molecules are vibrating. Water is evaporating. Clouds are forming. Currents are shifting. Magnetic field lines are guiding charged particles around the planet. And yet from the surface it feels calm. The sky appears still. The ground beneath your feet feels solid. But beneath that stillness is constant exchange. Earth does not resist cold through force. It remains temperate through balance. Incoming energy and outgoing energy are matched not by a single barrier, but by a network of interacting processes across scales, from atomic vibrations to planetary motion. Distance sets the stage. Rotation moves the light. Atmosphere reshapes the heat. Water stores and releases it. Geology regulates it. Magnetism preserves the system. All of it unfolding quietly, without pause, keeping the planet far from the frozen silence that surrounds it in space. Not protected by a wall, wrapped instead in physics. At every second of every day, Earth is radiating heat into space. An invisible glow rises from oceans, forests, cities, deserts, and ice. Infrared photons leave the surface and move upward through layers of air. Some pass through atmospheric windows directly into the vacuum. Some are absorbed and re-emitted along the way. But eventually, the energy departs. Space receives it. The vacuum does not push cold inward. It does not reach down and pull warmth away. It simply provides a destination for outgoing radiation. Earth shines steadily into that darkness, balancing the sunlight it absorbs. And yet, despite radiating constantly, the planet does not freeze. Because at the same time, sunlight is arriving. Light crosses 150 million kilometers and reaches the upper atmosphere. Some is reflected by clouds and ice. Some is absorbed by land and water. The absorbed portion warms the surface. The warm surface emits infrared radiation. The atmosphere reshapes that emission. The oceans store part of the input. Rotation redistributes it. Winds carry it. Clouds adjust it. Geological cycles regulate greenhouse gases over deep time. The magnetic field preserves the envelope that makes all of this possible. Nothing is static. Nothing is sealed. Energy flows through the system continuously. Earth is not insulated from space in the way a thermos insulates from air. It is open. It exchanges energy freely. The balance is not achieved by blocking heat from leaving, but by slowing and moderating its departure just enough to match the steady input from the sun. If too much energy left, temperatures would fall. If too much accumulated, temperatures would rise. Instead, the planet hovers near equilibrium, not perfectly, not immovably, but persistently. Night falls, heat rises, morning returns, seasons shift, ice advances and retreats, oceans absorb and release. Over billions of years, the same quiet accounting continues. Earth does not remain warm because space is not cold enough to matter. It remains warm because sunlight, atmosphere, water, rotation, geology, and magnetism cooperate in a layered system of exchange. The difference between frozen silence and temperate stability is not dramatic at any single moment. It is found in small, continuous interactions. Molecules absorbing radiation, water storing heat, winds redistributing energy, rocks cycling carbon. A narrow band of conditions holds. Not too cold, not too warm. Just balanced enough for oceans to remain liquid and air to remain thick. And as Earth turns beneath the sun, radiating softly into the darkness, that balance continues. A steady conversation between light arriving and heat departing, unfolding quietly above and below every horizon. A planet wrapped in physics, shining gently into space, holding just enough warmth.